Hi, my name is Scott Simpson, and today we'll be talking about atomic orbitals. Now, atomic orbitals are important for most of chemistry because you must understand the atomistic model before we can move on to higher things such as molecules. Atomic orbitals fall out of quantum chemistry, and you may need to review quantum numbers to get an idea of what's going on, maybe before or after this tutorial. Also, you'll need to remind yourself about the superposition of waves. We can do that really quickly. So, if you remember, waves can have constructive and destructive interference. So if I have two waves that are similar to this, and we end up superimposing them or adding them together, what we're going to get is something with double amplitude, where our crests and troughs meet one another. But let's say we shift these just a little bit. And what we end up happening is if we have wherever, in our first wave, wherever we combine it with an equal amplitude, but just displaced, if you notice this trough here, well, this crest and this trough meet up. So if we add these together, we actually get no wave. That's very similar to what's happening with electrons. Electrons can behave as a particle and as a wave. It's the particle-wave duality of an electron. That was a big deal in the past, which still should kind of be a big deal now. But so we need to have an idea of what these atomic orbitals look like. And these come from probability density maps from quantum. They have to deal with wave functions. So what ends up happening is you take the probability density based upon the wave function, and the wave function describes how an electron moves in an atom. And what you end up getting are these cool little orbital plots. And I apologize because I only have a two-dimensional board, but these actually exist in 3D space. So for our s orbital, what we have is kind of a big beach ball, a sphere of charge. Then when we move to the p orbitals, there are 3 p orbitals that are degenerate in energy. And what I mean by that is they have the same energy. So we have one extending up that way, one extending to the side, like that. And then we also have another p orbital that is in the plane of the board, so it's kind of hard to see, but something like that. That's extending into the board. I kind of try and draw a projection so you can see through the board, but it may not be so good. And if you notice, these have a positive and a negative end. And I'll talk a little bit more about that in a second. Now, these p orbitals almost look like dumbbell shapes, which is kind of neat. But they have a positive and a negative end to them. And the reason for that is it just comes out of quantum that way. And if you were to look at these, you could have constructive and destructive interference. Wherever you have a positive side and it overlaps with a positive side, you're going to end up with a higher amplitude or constructive interference. Wherever you have a negative and a positive side meet up, you're going to have destructive interference, so you'll have no overlap there. Now let's talk about the d orbitals. The d orbitals look something similar to these dumbbell type shaped p orbitals, but actually they kind of look like a butterfly. So you have to somewhat define your axes too. So let's call, so you'd have a plus, plus, minus, minus. And the d orbitals have 5 degenerate orbitals. So they'd have one like that. They have one that is directly up and down. And there are three in total that are similar to this. So we have 3 of these guys, 1 of these guys, and we have what's called the dz squared. And that one looks pretty funky. Like that. And it depends on your axes, but let's just call this axis the z-axis, and this one the x-axis. So this one would be known as the dxz. And the reason what we denote is we have our orbital and we have what direction our orbital is in. So if we were looking at something similar, let's call this the z-axis for p orbitals and this the x-axis. Since this p orbital extends up to the z-axis, this would be known as the pz orbital. In this case, since our orbital is going along the x-axis, we would call this the px orbital. And we're going to assume our y-axis is going into the board, so this would be known as our py. So that's how you go about naming these orbitals. But what you really have to know is there is one s orbital, 3 p orbitals, 5 d orbitals, and so on. If you review quantum numbers, there's an explanation on why we have 3 p orbitals and so forth. So review that if you need to. I think that's all there really is to talk about these orbitals. So if you have any questions or comments, please ask. If you review your textbook, you should have better pictures of these that are better 2D images. But you can also find some useful software on the internet. Like I think JMOL does some stuff where you can actually look at the orbitals in 3D space, which may be helpful for you to visualize it inside your head. I hope I've been helpful, and if you have any questions or comments, please leave them below. Thank you very much, and have a great day.